Alright, so the current way in which you've been taught to draw Lewis structures will look something like this. So let's say we have the molecule C6H. No, we're not going to do that. That's too many molecules. Let's say we have the molecule C2H6. Okay? You would draw out both C's and you would connect them. Okay? And then the next thing you would do is you would draw on the hydrogens. Like this, and you'd have all the hydrogens. Now, each of these bonds that you have here, okay, each of these, that represents electrons. So if you wanted to draw out the entire structure, you could draw something that would look like this. Now you could also draw the electrons looking like this instead. Like that. That's another way you can do it. But basically what I'm trying to show you is that these here, the red circles, these and this, they're equatable. So it's just a line there. Now if you want to draw a skeleton structure, you are not going to include any carbons, okay? Skeletal structures don't include carbons or hydrogens. So what this skeletal structure would look like, a line, okay? Each end of the line represents a carbon, and at every carbon, unless otherwise stated, there are 3 hydrogens. So let's try a more complex example. All right, let's try a carboxylic acid. So that's C double bond O-OH-H. Okay? If you want to pause the video here and give it a shot, you can go ahead and do that. But I'm going to show you how you would do this. So basically what you want to do is you want to get rid of this carbon. Okay? Now, in essence, what you're going to end up doing that's the skeleton structure you'll have. You'll see that the only point at which there was a carbon, there's now nothing there, and that would be representative of having a carbon there. So instead of a carboxylic acid, let's go ahead and try just C double bond on a ketone. So what do you do for this structure? So you want to do again is you want to get rid of the carbons while preserving the remainder of the structure. So what you're going to do is between a carbon to carbon bond that is longer than 1 long, you'll make a bend. Okay? So here's 1 carbon, here's 2 carbons, here we'll have an oxygen, and then we'll bend down again, and there's the 3rd carbon. 1 carbon, 2 carbon, there's the 3rd carbon, 1, 2, 3rd, and you have the oxygen between them. Now on carbon number 2, this carbon right here, there is an O double bond. Now an O double bond is significant because it's not a hydrogen and it's not a carbon. So we'll go ahead and put that in there on the 2nd carbon. Okay? Let's try another example. Let's say you have C-C-C-C-C, and I'm not going to draw on all the H's here, but on every line like this, the H that I drew here, we can assume that there'll be an H like that, okay? So I'm just going to put all the lines in there, and that's denoting that there would be an H. How would we do this kind of a structure? I hit the recording thing right there, sorry about that. So you want to count the amount of carbons that you have. So we have 1, 2, 3, 4, 5 carbons, okay? So we're going to draw a structure that gives us 5 points, okay? So we have 1, 2, 3, 4, and 5. And this will denote carbon 1, 2, 3, 4, and 5. And each point in the structure is denoting a different carbon, okay? You notice how all the carbons here have hydrogens on them? Since all the carbons have hydrogens on them, it's not necessary to go ahead and show like this. with H's that there is a hydrogen on each of them. Here we'd have 2 hydrogens. Here we'd have 2 hydrogens. Okay, and if you weren't aware, carbons will always form 4 bonds. Okay, it'll have 1, 2, 3, and 4 like that. So that's in essence how you want to go ahead and draw a skeleton structure. Now I'm going to go ahead and do a couple more examples with you so you can understand how to do it better. So let's go ahead and say we have a 7 carbon chain. Okay, and off of each of these is a hydrogen so far. But then let's say we have an oxygen here, we have an OH group. Okay, then we have an NH2 group. Okay, we have more hydrogens, and that's the remainder of the molecule. How would you go ahead and draw this structure? Well, since the goal of a structure such as a skeleton structure is to remove ambiguity and basically just get rid of the carbons and the unnecessary hydrogens such as this, you're just going to count the amount of carbons, which is 1, 2, 3, 4, 5, 6, and 7. So you want to make a skeleton structure that goes 1, 2, 3, 4, 5, 6, 7. Again, each point on the edge is representative of a carbon. Okay, now on carbon number 4 and on carbon number 5, there are 2 significant molecules. Okay, we have an OH group on carbon number 4, we have an NH2 group on carbon number 5. Okay, so carbon 1, 2, 3, 4 right here, we're going to have an OH group. Wow, I stuttered that. Oop. And on carbon number 5 here, we're going to have an NH2 group. Okay, and that's basically how you would want to draw a structure like that. Okay, now let's take a chain of carbons and let's attach a carboxylic acid to the end of it. And hell, let's put a carboxylic acid on the other end of it too. Actually, no, we'll put, instead of carboxylic acid, we'll put an aldehyde. And on the rest of these, you could tell that there would be hydrogens. Okay? What would you do here? Okay, well, the first thing that you would want to do is you want to count your carbons again. So we have a 4-carbon chain. Okay, so you want to draw a chain that has 4 carbons. 1, 2, 3, 4. Okay, now carbon number 1, we have a double bond O group and an H group. This is significant because it's an aldehyde. That's a functional group, which we went over in a separate lecture. Anything that has a functional group attached to it is significant. So on carbon number 1, we have a double bond O and an H group. The H is significant because it's part of the aldehyde functional group. On carbon number 4 here, we have a carboxylic acid. Okay, so we have a double bond O and an OH, which are both significant groups. So in essence, what we've done is we've removed this portion, and we've instead denoted that with these 2 carbons on the chain. And then instead of having this carbon here, we denoted that with a single line there, and we denoted that with a single edge there. Every edge in a skeleton structure, such as this, is denoting a carbon. So an edge here, that's equivalent to a carbon. This is the equivalent structure. Each edge has a carbon, and each edge would have 3 hydrogens. But we don't show those hydrogens. And that's just because they're repetitive.